Alright, this video we're going to talk about VIRPEt, or the terms listed here: voltage, current, resistance, power, energy, and time. And we're going to use VIRPEt and a couple of different rules and equations to help us analyze basically any circuit as long as it's only made up of batteries and resistors and switches. So, let's talk about the first term, voltage. The term voltage represents the amount of energy that each charge experiences in the circuit. Things that provide voltage are batteries and outlets. The symbol for voltage is V, and the units are volts, which is also abbreviated as V. Current is another thing. This is the amount of electrical flow in a circuit. So basically how much electricity is flowing through a wire or through a resistor. The symbol for current is I. I don't know why that is, it's just what it's used. And then amps, or amperage, is the units labeled as A. So current is I, labeled as amps. Resistance or load is the resistance to flow. It's basically like how much effort it takes to get through a device in a circuit. Resistance is labeled as R, and then the units are ohms. And this is a symbol for ohms. Power is how much power it takes to power the circuit, or how much energy it uses over time. The symbol is power, or P, and then watts is the unit for power. Watt, labeled as W. Energy is just how much energy the circuit uses, or how much energy the device uses, labeled as E. Used for energy is joules. And then time is obviously how much time the circuit is operating in seconds. Now there are three equations and then two concepts which will help us analyze any type of circuit. So any type of circuit that I throw at you, you can use these 5 key points to analyze them. The first one is that V equals IR. This is Ohm's law. It says that the voltage used is equal to the current times resistance. So if I take amps times ohms, I get volts. The next equation is P equals IV. So power is equal to current times voltage. Power is also equal to energy over time. That's the definition of power, so we can use that as to figure out energy. The last two are actually just concepts. These are Kirchhoff's rules, or Kirchhoff's laws. One law says that the current into any section of the circuit equals the current out, and we'll talk about that in more detail. And then the second one says that the voltage in any closed loop gets used up, and we'll talk more about that in detail too. So what I want to do is use these 5 rules and concepts to analyze any circuits. And the first circuit we're going to build is just a real basic one. So I'm going to VIRPEt, which is an online circuit builder. I'm going to start with just a single battery, and then I'm going to connect a wire to it. And then we're going to use light bulbs as resistors. So I'm going to do one light bulb, hook it up to another light bulb, and then connect the circuit to the other side. Now I'm actually going to, the lights of both light bulbs, I'm actually going to go to connect conventional current here. So as you can see, the positive end of the battery is always denoted with a little different color. If I do the schematic here, here's what a schematic looks like. These would technically be resistors, they're labeled as light bulbs. But the positive side of the battery, current leaves the positive side of the battery, goes through this light bulb, and then it goes through this light bulb, and then here, let me actually add a switch in here as well. So now I can actually like open and close a switch. Close switch, open switch, it can't go through. So when I close the switch, let's just see if it can go through. So then the circuit schematic, what it looks like, with an open switch. These could be resistors as boxes or jagged lines or light bulbs. I'll close the switch again. So what I want to do is I want to analyze, I'm actually click on values here. So I know that the voltage is given by the battery, and this is the amount of resistance for each light bulb. So the cool thing is I can use these 5 ideas, V equals IR, P equals IV, P equals E over T, current in equals current out, and voltage gets used up in a loop, to basically answer everything about any circuit, as long as it's just made up of batteries, resistors, wires, and switches. So basically, I can analyze any type of circuit with those components, as long as these are the only things in there. So let's get started with this one. What I did was I made a little table here. Since we only have two resistors, I only labeled resistor 1 and resistor 2. It doesn't matter which one's which, you just have to assign. Maybe this is resistor 1, resistor 2, or maybe this is 1 and 2. It doesn't matter as long as you keep them noted. And then I have a column for total resistance. It's always good to have a column for total resistance. You don't necessarily need it all the time, but sometimes it helps you to do some math. And then I made a little table, VIRPET. Voltage, current, resistance, power, energy, and time. It spells out VIRPEt. It's kind of like SUVAT, but there's fewer equations to know. And the cool thing is, I can start filling in some of these values. Because if I look back at this circuit, let's start off with what do we know? Let's go with resistance. I know that this resistor is 10 ohms, it's labeled. This resistor is 10 ohms, and this battery is 9 volts. So where does this go? Well, I don't know how much ohms or voltage that resistor 1 gets. Let's start with the resistance. It was 10 ohms. I'll put that in there. Resistor 2 is 10 ohms. Total resistance, if they're in series, I can just add them up. So the total is 20. Going to the voltage, I don't know how much voltage that this resistor uses, or this resistor, but I know that the total voltage has to be the voltage of the battery. The battery's voltage was 9 volts. So I would just put 9 for the total. I won't put total resistance, I'll just put total. I'll put 9 for the total. And then it seems like my table is completely filled up with numbers from the circuit. So then what I could do is I can use these rules. And I always like to start with the first one. V equals IR. And the cool thing is, if I know V or I can figure out R or vice versa. And if I know two of these variables, I can figure out the third one. Well, then I look at this table, and I look at which column do I know the most information. I know the most information about the total column. I know V and I know R, so I can figure out what I is. I would just equal V over R. Just rearranging that first equation. So if I do that, I would get 9 over 20, or 0.45 amps. Awesome. Now, what I can do is I can go down, next thing I like to do after I use V equals IR, I can use P equals IV. Well, do I know P? No, I don't, but I do know I know V. So P equals IV. I can basically fill in the rest of this column if I wanted to. P equals IV. And I would say, all right, well, P equals IV, that will be 0.45 times 9. Let's go to a little Google calculator here. 0.45 times, type here, looks like, times 9, 4.05. So I know that this uses 4.05 watts. Let's start putting units here. It's to be ohms, it's to be amps. So right now I find the total for the whole circuit. Volts. Energy. Now in order to figure out energy, I need to know how long this circuit runs for. So I don't know. I mean, the longer I run the circuit, the more energy it's going to use. Let's just say I run it for a minute. If I run it for a minute, that means that I would have to put in 60 seconds under my time. Well, now I can use, to figure out the energy it uses in joules, I would just rearrange this equation and take E would equal power times time. So E would equal power times time, and I would get 4.05 times 60 times 60. It equals 243 joules. So look at that. I already have all of the information from the total amount of from the total values for this circuit. I know the total voltage, total amps, total ohms, total watts, total power, total joules it uses, and how long it operated for. But let's say I wanted to know like how much this particular resistor uses, or this particular resistor. I need more information to fill in some of these values. But the cool thing is, I can go up to some of these other rules, Rule 4 and Rule 5, to kind of answer these questions. So let's talk about Rule 4. Rule 4 says that the current going into any section of the circuit equals the current going out, which means that if the circuit doesn't split, that current's going to be the same. So let's say that we had like 1 amp of current leaving this. It's not going to be 1 amp, it's going to be something else, but if 1 amp of current leaves this battery, it goes around, 1 amp is going to enter this part of the circuit, it's going to leave this, it's going to enter this 1 amp, and then 1 amp is going to get back to the other side of the battery. It's only going to not be 1 amp is if there's multiple paths. For example, if I take this wire here and I give the electricity another path to take, like this one, now obviously that 1 amp can change if there's multiple paths like that. So what we need to do is we can use this idea and figure out, well, going back to our table, we know that the current leaving the battery is 0.45 amps. So we can go back to our circuit and say, okay, 0.45 amps is leaving the battery. That means that this has to be 0.45 amps because there's no other path that the electricity can take. Let's say there's 0.45 gallons of water leaving a faucet. All 0.45 gallons of water have to go through this little spigot or faucet or device here, and then all 0.45 gallons of water would go through this device here, and then it gets back to the other end. So it's conserved. So as long as it doesn't split into different paths, as long as there's only 1 path to take, that 0.45 goes to both of these because it entered both. Now you notice the total doesn't add up. 0.45 does not equal 0.45, but it's the idea that does. The total current goes to both of these. This one gets the total current, and this one gets the total current. So sometimes the total, you can't just simply add them up for every single scenario, but sometimes you can. And we'll talk more about that in more examples. Now that I have 2 pieces of information, I can go and fill the rest. Let's just go to V equals IR. I want to figure out how much voltage this one uses. So the voltage for this one would be I times R, which essentially would be 0.45 times 10, which is 4.5 volts. Let's lay it 4.5. This one would also be 4.5 volts, similar argument. I can go through and figure out the power by taking P equals IV. I would multiply this by this, and then I would get 2.025. I'm taking that times that, 2.025. You're probably wondering how I'm doing that so quickly in my head. This resistor right here, if the whole circuit's running for 60 seconds, that means that each part of the circuit's going to run for 60 seconds. So that's going to run for 60 seconds. This is going to run for 60 seconds because, once again, the total doesn't add up. It's just however much time you run it for is the amount of time that each thing operates for, as long as you don't turn it off. The energy for this one would just be 60 times the power, which looks like 121.5 and 121.5. So the reason I was able to do that so easily in my head is because I know the total power has to be 4.05 watts, and each of these have the same resistance and the same current, so I know that they have to have the same power, and I know that each of them have half the voltage, so I basically cut this number in half, so they each split it in 2. Same with the energy. That was just a mental math thing I did. So now I know everything about this circuit. I know that this resistor is 4.45 volts, this one has 4.5 volts, this one has 0.45 amps, this one has 0.45 amps. I know how much energy and power they use, and let's actually check that. I'm actually going to go back to the circuit and check that using a voltmeter and an ammeter. I'll actually check those values to see if they're correct. So the way a voltmeter works is I just basically take it and I touch one lead to one end of the device that I'm trying to measure, another lead to another end of the device, and it's reading a negative, and if it's reading negative, I just switch the ends, and it reads a positive, so it doesn't matter. I just want the absolute value of this. So 4.5 volts. What did our table say? Yeah, 4.5 volts. All right. Then I can measure the other one too, and it gets 4.5 volts again. So I was right. We calculated right. The first one used 4.5 volts, the other one used 4.5 volts. Let's double check our current. So the current, this ammeter here works pretty well. It's just virtual, so I just hover over it. The current's reading 0.45. Everywhere in the circuit, it's reading 0.45. It doesn't matter where I go, it's reading 0.45 amps because there's only one path for the electricity to take. So of course it has to work. According to this rule right here, the current into every section of the circuit has to equal the current out. So since there's only one path, every part of the circuit has to have that same current. Let's look at this fifth rule. Just verify this fifth rule. The voltage in a loop gets used up. What does that mean? Well, here we only have one loop. There's only one possible loop that we can make. It's this loop right here. Starting with the battery, it makes this loop, and it completes a circuit. There's no other path that I could take. For example, if I were to add like another battery or another device here, such as this. So now I want to connect something like this. Electricity can go this way, or when it gets to this point, it can go this way. So it has multiple paths it could take, and since it has multiple paths it could take, the current's going to split. So whatever current this is, let's find out what that is. It'll be a little bit different than last time, 0.18 and 0.36. Those are different, but the cool thing is 0.36 and 0.18, they have to add up to the total current of 0.54. This is a different circuit than what we just did, but I'll get the regular circuit back that we did. There you go, I basically shut this one off. Actually, let me do this. Okay, so now this one is shorted, so I don't need that. But anyway, so this one, the current in every single path is 0.45. It doesn't matter where I go, because there's only one path to take. It can't take this path. But this last rule here also says that the voltage in the loop gets used up. So what that means is that there's only 9 volts available. So this is only one loop, so all 9 volts has to get used up. Well, this uses 4.5 volts. This uses 4.5 volts. So 4.5 volts get used up here. 4.5 volts get used up here. By the time it gets back to the other end of the battery, it's lost all its voltage. So it gets charged back up and then leaves the battery with 9 volts. 4.5 volts gets used up here. 4.5 volts gets used up here. Goes back to the battery. It's discharged. This gets charged up again, and it just completes the circle. And that's the cool thing about circuits, is that that rule has to apply no matter what the circuit is. Let's try a slightly harder one this time. This is an example of a parallel circuit because it's parallel paths. There's more than one loop that it could take. It could take this loop, it could take this loop, it could take this loop. And these light bulbs have different resistances. This one's 40 ohms, 60 ohms, and 120 ohms. Right off the bat, you know, and there's 2 batteries. But right off the bat, you notice that the 120 ohms, the highest ohms, is the dimmest light bulb, and the one with the least amount of resistance is the brightest light bulb. It's because it takes more energy to go through this light bulb than it does this one. It's a lot easier to go through this light bulb. So let's go back to our VIRPEt table. I added another resistor here, resistor 1, 2, and 3. Let's just go from left to right here. Just like we did last time, we'll call this resistor 1, resistor 2, resistor 3. Let's fill in what we know. We know resistor 1 is 40, resistor 2 is 60, and resistor 3 is 120. So 40, 60, and 120. Now, this time we can't actually add up the resistances because, and we'll find out why in a second, when there's resistors in parallel, they can't add the resistances. And there's a rule to figure out the total resistance for parallel circuits, but we do not know what the total resistance is because since it can take multiple paths, the resistance actually goes down a little bit. But we do know what the total voltage. Total voltage is just the voltage supplied by the batteries, and that's going to be 18 this time. So the total voltage is 18. Now, this is where it becomes tricky because that's all of our information. We cannot simply add the total resistance this time. We cannot add the total resistance in parallel. That's one rule to follow. Maybe even add that to another rule here. And that kind of goes off of these two rules, but maybe like a little side rule. Resistance in parallel does not add to total. All right, and that's based off these two rules, so we'll elaborate on those. So what we have to do is we can't use these equations right away like we did last time. We have to use these two rules to help us fill in some information. Well, rule number 4 says the current into any path is equal to the current out. So what that's saying is if I find the current into this path, this is 0.9. But then once it gets to here, it can split to this path, which is 0.45, 0.3, and 0.15. So 0.15 plus 0.3 plus 0.45 is equal to the total, which is 0.9. Now, if I didn't know that, if I didn't actually measure that, I wouldn't be able to like plug these numbers in. So I'm going to come back to that. But basically, that rule does apply, but I wouldn't have known those numbers without measuring them. But there is something I do know without actually measuring anything. Because of rule number 5, the voltage in any loop gets used up. Here's what that means. What I can do is I can draw a little loop right here. This loop right here, the total voltage is 18 volts, and all 18 volts go through this loop. There's a path for that 18 volts to take, so that means that everything in this loop has to equal 18 volts. Whatever device is in this loop has to use up 18 volts. So let's just double check if that's true. If this resistor right here, since there's only one, it equals 18 volts. Look at that. Resistor 1 uses 18 volts. What about resistor 2? Well, there's another loop here. This is a little bit bigger loop. You see this middle loop right here? That is another loop. And what that 4th rule or 5th rule says is that this loop also has to use up all of the voltage, 18 volts. Because voltage is the amount of energy per charge, so you can have the total voltage not equal the voltage of each loop. Basically, each loop has to add up to the voltage of the battery, because if there's 18 volts leaving, that means that by the time it gets back to the rest of the battery, all 18 has to get used up so it can get recharged again. So that means that this loop also needs to have 18 volts. And it does. We can say the same thing for the last loop. This big loop right here also needs to have 18 volts. Let's just double check. And indeed it does. So all of them actually get 18 volts. Now the reason that the voltage doesn't add up to the total is because voltage, if you remember, is the amount of energy per charge. And so basically, since it's not talking about total energy, it's just talking about energy that each charge has, you can imagine like 3 electrons. The first electron takes this path and it has 18 joules of energy. This electron takes this path and has 18 joules of energy. And this electron takes this path and has 18 joules of energy. Each electron took a different path, but they all had to use up the energy that they were given before they get back to the destination. And then once they get back to here, they used up all 3 of them, used up all their energy, and then they get recharged again. The battery kind of recharges them so they can go off on their own adventures. They each take their own different adventure, but they all come back to their starting spot and need to get charged up again. Going back to our data tables here, now that we have 2 pieces of information here, voltage and resistance, we can use our equations to fill in the rest of the information. So I can use V equals IR to fill in the rest of this information. I can do I would equal V over R for all 3 of them. And in which case, I would take 18 over 40 to get, well, what's 18 over 40? .45. So this would be 0.45. This one I would take 18 over 60. It's 18 over 60. That's 0.3, I believe. Yep, 0.13 or 0.30. 18 over 120, that's going to be 0.15. Now, the cool thing about this is that we already measured these. If you remember that, we already measured what they were. This was 0.15, this was 0.3, and 0.45. All three of these, according to this rule right here, current in equals current out, they all branched off. This branch, this path, and this path, they all split apart from this path. This path was like the initial waterfall, if you will. It's split into three separate paths. This one, and this one. So total is 0.9 amps. You can imagine it's like 0.9 gallons of water leaving the faucet. And 0.9 gallons of water split up into 0.45, 0.3, and 0.15. They have to split up, and then they come back together at this intersection, and they get back to 0.9. So the total here, we can actually just add up and get 0.9. Let's be consistent with that. So now I can actually fill in the rest of this table if I wanted to. I would just use R would equal, well, rearrange this equation. R would equal V over I, the total. Well, V would be 18 over 0.9. 18 over 0.9 is 20. So the resistance is actually 20. So look at this. The resistance actually does not add up to the total for parallel. There is actually an equation for this to find the resistance in parallel. It says 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So if I took 1 over 40 and added it to 1 over 60 and added over 1 over 120 and then hit equals, and I took 1 over that number, I would get 20. And we'll talk more about that later. Now, if I wanted to, I could figure out the amount of power it used, or each resistor using I times V, and the amount of energy it used if I used E over T. Let's say that this ran for 60 seconds. That means that each one also runs for 60 seconds, because it's not like I could run one resistor without running the other three, or other two. And then I would just use P equals IV for each part, so I would do I times V. So 0.45 times 18 8.1, and then I could just continue the rest of this table. So I went ahead and did all the math for you. Basically, I found the P's by using P equals IV for all of them, and I found the energies by using energy equals power times time. Just rearranging these equations right here. The cool thing is with these, you can check all your answers. The current has to add up to the total, so if I take this plus this plus this, that's equal to the total. At least for parallel. The power has to add to the total, so if I take 8.1 plus this, I get the total of 16.2. The energy has to equal the total. Now, I want to highlight a few that don't have to add to the totals. The time will never equal the total. Basically, each resistor is going to just equal the total. You don't add them up. Energy, this column, you add up every single time. Help check your answer. Power, you can always add up to find your total. These three are kind of interesting. Resistors, you add up if it is only one loop, but you don't add up any other time. If any other time, you have to use either this or just puzzle solving. This one, you add up if it's only one. Oh, you add up if it's multiple loops. This one had multiple loops, so it added up. If there's only one loop, then they just get the total. So it gets total if only one loop. This one, you don't add up if it is multiple loops, but you do add up if it is only one loop, like in that first example. So hopefully those will, this is kind of like a puzzle. I really like this VIRPEt table because it's kind of like a puzzle. As long as you follow these rules, especially V equals IR, current in equals current out, and voltage in loop gets used up, as long as you can remember those three rules, the rest of it just falls into play. This is just a plug-and-chug calculation. This is a plug-and-chug calculation. These are just kind of applications of rules 4 and 5. Essentially, like, this is just stating that number 6 because it's following these two rules mathematically anyway. Alright, so to end this video, I want to talk about a more complex circuit, something kind of like this one, where we have a small loop here and like a bigger loop there with 15 volts total and then a small loop and a bigger loop. Let's say we ran this circuit for 60 seconds. That means that every single resistor in that circuit is also going to run for 60 seconds, because if you remember that you don't add the time up, it's just the time for all of them. It's not like you can turn off one light bulb and then the other ones would light. They're all running for 60 seconds. Now looking at this circuit further, we can see that the total voltage is 15 volts. It's just the 10 volts plus the 5 volts from the battery. And we do know the resistance of each one. Let's say this is 1, 2, and 3. It'd be 8 ohms, 15, and 10. So I can put that in, 8, 15, and 10. Now if you remember, we can't simply add the total resistance because they're not in one loop. So the next thing we can do is our goal is really to figure out V, I, and R for everything. And I don't have enough information to use V, I, R for anything because I don't know I or V for the resistors, and I don't know I or R for the total. But I can use the other rules because there's loops here. There's a loop right there, and then there's a bigger loop right there. And if I look back at my rules, there is that one rule that says that the voltage in every loop gets used up. So if I measure this voltage, it should say 15 volts, because that smaller loop is using all 15 volts. The bigger loop also should get 15 volts, because the total voltage gets used up in each loop. If I measure the voltage of the small one, it's 6. If I measure the voltage of the big one, it's 9. That totals 15. So I can go back to my table and put that 15 volts back in for resistor 1. And I did measure resistor 2 and 3. I got 9 and 6, but without measuring them, I wouldn't have gotten that. But the good news is I can go to I, because I do know V and I know R for that first resistor, and I can use good old V equals IR to get I, because I essentially is just V over R. And so that would be just 15 over 8, which is 1.875. And I can go over to my simulation and check it with the ammeter and measure it. And indeed, it says 1.87. It's rounded, so that kind of confirms we were right there. Now, if I wanted to, I could actually calculate the power and energy because I have I, V, and R for that resistor, and I can use P equals IV and V equals IR. And the cool thing about power and energy is I can always add up to find the totals, because that's a good way to check your work, because the power and energy will always add up to the total. So you can always check your work that way. So now, we did make some measurements so we could fill in some more of the table, like the resistances, the voltages, and the current. We can make some measurements to get those. But there are more techniques that we'll go over in the next video of how to fill in the rest of this table. But basically, this ends up just being a puzzle, like a Sudoku puzzle. Once you start filling in more information, you can use the random pieces of information that you found to fill in more information. Like, oh, since the current was this in this box, I know that the current has to be this in this box, etc. So we'll go over more depth of that next time, so stay tuned.